Okay, guys, so this is problem number 70 from chapter 2, exercise. And in this problem, it says that the water drops falling from the edge of a roof. So there is a building. Okay, so let's, of course, you can imagine if you have like water drops falling, it is freely falling. So it's basically again problem of a free fall. You are probably noticing a lot of problems coming from free fall motion. The reason behind this is that you're going to see a lot of these scenarios in the subsequent chapters. So it's very important for you to understand how these kind of problems work. Okay, so if you note that this is a problem for water drops falling from the edge of a roof. Second thing that you note that we are dealing with free fall. So this is a free fall motion. Every time you encounter free fall, you will have to think about AY equals to minus 9.8 meter per second square. Okay. So if we want to now draw or sketch the problem, we can simply again draw a vertical line. Okay, and again we can now decide which way would be our origin. In previous problems we have taken always origin to be at the bottom, but it will not work because the droplets are falling from here. So it's wise to have the origin right here so that you can use the negative part of the y-axis for this problem. Okay, so it says that if you have, there are like 5 water drops. Okay, so there's one here, another here. They're all like equally so this is the 5th drop, this is 4th, this is 3rd, this is 2nd, and if I extend this a little bit, this is our first drop of water that came down, right? So again, we have chosen a suitable origin. It is probably convenient to choose origin at the top. Let the height of the roof be h. Okay, so let's say this height is, this length is basically h. But if you want to like write it down in coordinate space, then you would write y equals to minus h at the bottom, right? This is the negative y-axis. If you have to specify the y-axis, sorry, this is y prime. Remember, if you had coordinate axis, this is y prime, this is origin, sorry, what am I writing? This is y prime, this is x, this is x prime. We're working with the negative y-axis here. Great. So if we take delta t, now all these droplets, there is another thing in this problem. There is a window here, right? There is a window, and at the bottom of the window you have the second drop, at the top of the window you have the first drop, and the distance between these two drops is 1 meter because that's the length of the window. So this is like another additional information you will need to solve all the variables. Now if you think about the equal time intervals, right? All these droplets are falling with same time interval, equal time intervals, okay, between themselves. So if you choose, if we take delta t to be the time interval between the drops, okay, in which the drops are falling from the edge, between the drops that are falling, then we can say that the first drop, well, we can say that this is time equals to 0, right? So the fifth drop has not started falling at all. Fourth drop has been falling for a time of delta t. Third drop has been falling with a time of 2 delta t, right? Because they're all equally spaced, and the earlier they have dropped, the more distance they have covered starting from origin. So you can see this is 3 delta t for the second drop, and finally the first drop has been traveling for 4 delta t, right? So if we now we have like a series of times to work with using the kinematic equations. Now we can use the kinematic equations to find out, basically we're using the position equation, okay, yf equals to yi, yf equals to yi plus vy delta t plus half ay delta t squared. You can even call it vy1 or something like that. But we are going to write it for all of these different water drops. For the third drop, you should be able to write it as y3 equals to 0, because it starts from y equals to 0. Then it starts from initial velocity 0, right? It's a free fall. So the second term also gives you 0. Only the third term is going to give you half times minus 9.8 times. And in this case, this delta t is basically 2 delta t, okay? So if you will get confused, do not use delta t here. Say just time interval. Do the same thing here as well. Times time square. Sorry, there is no square here. And then for the third drop, the time is, we have already seen, right? 2 delta t. So use 2 delta t. And now you have, and for the second one, you can have y2, which is 0 plus 0 plus half, again minus 9.8, and instead of now time, you have 3 delta t squared. Okay, so if you simplify these two, you can get basically 4.9 times 4 delta t squared, and then 4.9 times 9 delta t squared. So if I skip all those steps, basically what I'm trying to do here is y2 minus y3, right? And I'm going to get minus 9.8, or basically 9.8 by 2, so 4.9 times 9 delta t squared minus 4 delta t squared. Once we have that, on the left hand side we have these to be minus 1. Why? Because this is the length minus, this is the length 1 meter between these two guys, right? And remember, we are working with negative. So y2 minus y3 equals to minus 1 minus, and on the right hand side you have minus 4.9 times 5 delta t squared. If you solve for delta t from here, you are going to get 0.202 seconds. Okay, so This is quite crucial to understand the negative number here, because the second and the third, they are like subsequent, like consecutive droplets, and they are 1 meter apart, and we are using a negative number here because we are going to the negative y-axis. We have already discussed this before. So once we know delta t, then we know how long, for how long the first drop has been um, using for how long for the first drop has been falling, right? So using delta t, using the value of time delta t, now we can find out how far the first drop has fallen. And whatever that distance is, that is basically your height of the building, right? So for the first one, first drop, you can write y1 equals to 0 plus 0 minus half, again 9.8, the negative sign is taken care of here, times 4 delta t, right? So 4 delta t squared, and this will just be times 9.8 times 4 times 0.202 squared. Calculating that will give you minus 3.2 meters. Note the negative sign here. It makes complete sense to have y1 to be a negative sign, because y1 is right here, okay, and this is 0. So if you have traveled this way, this has to be a negative number. Okay, so with this, we are going to we have probably concluded most of the problems that we wanted to have solved from chapter 2, and I may come back, and or probably during the lecture on Monday I may just show you a couple more problems, or discuss at least, but that's needed to be seen. So goodbye for now. I'll see you in the next one. Alright guys, this is a video recording of chapter 2 lecture problems, and in this videos I'm going to solve the problems completely and upload it in YouTube. So we start with problem number 14. Those who already have attended the live session, they know that we have solve these problems during the class as well. So if you already have done it, so you can skip this part and go to the next one. All right, so in this problem it says that a jet plane is cruising at 300 meters per second when suddenly the pilot turns the engines up to full throttle. So if you think about the story, a jet plane was moving, and I'm just taking randomly to be along x-axis because it doesn't mention which direction it is going, but it looks like it's moving in a straight line. So you can just simply take a straight line coordinate axis. You could basically even label it as x, and then the next thing that you would need to do is to provide a reference frame. For that, read on a little more the problem statement, and then you will probably be able to decide which way it is better, where to take it. Okay, so the first information we see in this text is that it is moving at 300 meters per second. It is cruising at 300 meters per second. So it is talking about a velocity, right? And you could think about that 300 meter per second to be the very first information, very first picture that you see of that jet plane. So you could say, okay, if 300 meter per second is the velocity of the jet plane at that point, you could for convenience you could put your origin over there, so that you can start counting time and space or distance right from that point. Okay, so that's your very first take on the problem. We can change that if we read something later that prompts us to do it. After traveling 4 kilometer, the jet is moving with a speed of 400 meter per second. So after a certain distance, and that distance happens to be 4 kilometers, okay, the plane is moving now at 400 meter per second. What is the jet's acceleration in between these 2 points? So we are given a ti to be t equals to be 0. We are given also that xi to be equals to 0 because they both coincide with the origin. We also are given vxi to be equals to 300 meter per second, and we are also given that v xf to be equals to 400 meter per second. Now, you can also sometimes call it VFX or VXF. It doesn't matter. As long as you have the labels right, it all matters. Okay. F means final, X means it is along the x-axis. So if you're given all this information, oh, you also are given that X final to be equals to 4 kilometers. And if you convert that in meters, it will be 4,000 meter. So once we know all these things, what you need to find out, the question is, what is AX in this problem? If you think about the three, or take a look at the three equations, you know that equation number 1, 2, and 3. Number 1 works with velocities, number 2 works with distance or displacement, or initial and final positions, and third one is a one where you do not have a time involved. So in this problem, you do not know the final time, right? So TF is not known. So you cannot work with any equation that deals with time. So you can rule out 1 and 2 and choose number 3 to see if you can solve the problem just by one equation. There will be cases when you will not be able to solve the problem just by using one equation, but we will see that later. So the problem that we want to formulate is that Vxf squared equals to Vxi squared plus 2ax delta x. During the class, I might have taken a more general level. If you don't want to use x, you can always use s. Okay, so this would be VSF or VFS, VIS, and AS delta s. But generally, the equation will be very similar. So this is 400. This is 300. This is 2ax. And this is also 4,000 minus 0, so 4,000 basically. If you solve ax from this, you are going to get 8.75 meter per second square, and that kind of you can also take it to be approximately equals to 8.8 meter per second square if you want to round it off. Both are going to be fine. So the constant acceleration the jet plane is moving with is 8.8 meter per second square. Remember that even though there is no time given here, if you wanted to, you could actually find that time TF using the very first equation. Okay, so for example, if the question was what is the time taken by the jet plane in reaching or in covering that distance, you could easily use Vxf equals to Vxi plus Ax delta t, right? And then you know Vxf, you know Vxi, you know Ax now, which is 8.8 or 8.75. You could easily find delta t, and you know that Ti equals to 0. So all you need to find is Tf, and you would be able to find that. Okay. All right, so with this, I'm going to stop here and then we'll come back with the next problem video. Okay guys, so we're back with problem number 29 from chapter 2, and this is a problem where it is talking about a snowboarder gliding down a 50-meter long 15-degree hill. So the very first picture that we will have to think about in this problem is that you have, excuse me, you have an inclined plane, right? And I'm going to draw this straight line because we will need it later on. If you read on the problem statement, you are going to see that the snowboarder, and let's just project that the snowboarder's initial position to be right somewhere right here, so that the origin is over there, okay, and she glides down all the way to the end of the slope, right? This is a 15-degree slope, and you can call this to be theta 1 because there is another slope coming up, and then there is a flat region, okay, and then you have an uphill, and which is a slightly steeper inclined plane. So this is, I would call theta 2, and that's equals to 25 degrees, okay. Now we know that for inclined plane or motion on a ramp cases, you have acceleration if you talk about like a general level as, and it gives you plus minus g sine theta, right? You are going to need both of these two different signs for the acceleration in these two cases. For example, if you divide the whole problem in three parts, this is part 1, this is part 2, and this is part 3, then you would be able to see that in the first part, when you have an acceleration, the acceleration is actually helping the the person who is moving. It's helping the velocity, so it is going to, the person is going to speed up, okay. So she starts with 0, and I can call it VSI, okay, even call it VSI1. Actually, let's stay consistent with the one with whatever notations we use during the class so that you don't get confused. So for the first one, I would call it VI1, and it starts with 0, right? For the first part of the motion, theta 1 is 15 degrees, and the acceleration is away from the origin, so the acceleration is positive. So you will have to choose a S1 to be equals to plus g sine theta, or g sine theta 1, okay. So we know the initial velocity, we know acceleration, we also know something else. We also know that this length is 50 meters. So if your xi, sorry, it's not x, it's si, to be equals to 0, I1, you can call it I1, and SI, sorry, SF1 to be equals to 50 meters, then we have basically a delta S, right? SF minus SI, which is basically 50 meters. In the second part is very easy because the second part is a constant velocity motion or uniform motion, right? So whatever velocity the person has acquired at this point is going to stay the same until this point. So in between here and here, she will be moving with constant velocity, and after that she is going to go uphill. In that case, again, the acceleration, um, and this was as1, so this is as2, and that is basically minus g sine theta in this case, because now you have acceleration pointing towards the origin instead of, or towards the starting point instead of going away from it. So your velocity is in this direction, your acceleration is in opposite direction to the velocity. Here you had both velocity and acceleration along the same direction. Depending on that, you are going to choose the sign of, or which sign you are going to use for the acceleration in these three cases. So here you are going to use a velocity which is basically vf1, right? If the velocity starts here with vi1, it will become vf1 at the end of the first part, and it is going to stay as vf1 in the whole part of the second part of the motion, and that will be the initial velocity here. Final velocity is 0, and you already saw that acceleration, if you call it as2, should be minus g sine theta 2. Okay, so g sine 25 degrees. All right, so keeping that in mind, if we like go into the problem solving part, like the calculations part, before doing this, we'll have to also take a look at what we need to find out. The first thing is, what is the velocity at the bottom of the hill? Basically, this quantity, right? So A is fairly easy. If I write if vf1 square equals to vi1 square plus 2a s1 delta s, then we can write this to be 0, and this is 2g sine 15 degrees with 50, right? Once we solve vf1 from this equation, because g is 9.8, once we solve vf1 from here, we are going to get 15.93 meter per second, or 16 meter per second. You can call it 16 if you want. For the second part, we now know that the velocity has attained 16 meter per second here, and it was 16 meter per second here as well. So if you go to the next part, part B, your initial velocity over there is 16, your final is 0, so you can use the same equation, basically this equation, for the second part, but this time you will start with 0 square, and then here you will have 16 square, because that's the initial velocity over here. Then you'll write 2 as2. as2 is basically g sine 25 degrees, right? And then you are going to use the length for the second one, so delta s2, if I may call it. So you can call the first one delta s1 to distinguish between these two guys. Okay, so you can find, again, solve this for there is something wrong here. This has to be a negative sign because we have already chosen likewise. So anyway, if you solve for delta s2, you are going to see this is equals to 30.91 meters, approximately 31 meters. And so if you so that's basically the whole displacement part of the second slope that she was moving. So she started from here with 16 meter per second. She moved up until she got like stopped because of the acceleration working against her, right? So the acceleration AS2 is trying to pull her back, so that's why the velocity becomes 0 at that point. And then eventually she will, of course, will roll back if there is no other force or no other source of acceleration that can sustain her motion. So that's problem number 29. I'm going to stop here and then we will come back with another problem video. Okay, so we are back with problem number 56. This is the third problem from chapter 2 exercises. So here, if you read the problem statement, you're given like a 1000 kilogram weather rocket that is launched straight up. So you can clearly see that this is a problem with vertical, along the vertical axis. So you can safely start drawing or sketching your problem along the y-axis. Okay, so, and as always, you will have to think about where to put your origin. If your origin is here or somewhere here, we are going to see. We'll read on, and it says that the mass is 1000 kilograms. We don't know if we are going to ever use it, because so far any of your equations, if you look at any of your equations, you're not going to see a mass involved. Oh, apart from the density problems. Okay, so who knows? Let's see. The second thing that you might notice is that the rocket is launched straight up. So vertical motion, y-axis, we have already denoted that. Acceleration, there is an acceleration for 16 seconds. So the rocket is moving straight up for the first 16 seconds. It is accelerating, all right? And at that point, the motor stops. So these are the information that you are gathering from when you are reading the problem. Okay, so the final altitude, which is 20 seconds after the launch. So if the launch is here, now it has become clear that this has to be your origin. This has to be your Ti equals to 0. This has to also be your Yi to be equals to 0. Okay, so that's your very first point from where the rocket was being launched straight up. And then after 16 seconds, the acceleration stops, right? So when the external acceleration stops, then you have a free fall between here and then whenever the rocket, for whatever amount of time the rocket has been moving afterwards. So you should remind yourself that the acceleration along here is basically AY equals to minus 9.8. So avoiding the typo, let's draw it here so that we can clearly see this, minus 9.8 meter per second square. All right, so that's the acceleration for that part. So the acceleration is basically downward. Here acceleration is upward, so it was speeding up, right? And we don't know that acceleration. The acceleration is our question that is unanswered, and that's the problem that you have to solve. Okay, so this is a more complex problem. So again, we have just used a pictorial representation. Oh, it's also given that the maximum height is 5100 meters, and at 5100 meters, this is basically t equals to 20 seconds. Okay, so this is t equals to 0, and I don't need yet the i's and f's because I can clearly see this is like a sequential, right? These are sequential values, so we don't have to do a lot about specifying ti's and tf's. But if we want to set up the equations now, we would know that here you have v, the initial velocity, okay, is, if you call it v0, that is also 0, right? Because it started from rest. The reason that it started moving without having even a velocity at this point, at the very origin, is that it had an acceleration. The acceleration took it from 0 to a small velocity, and then the velocity went larger and larger and larger until the first 16 seconds. So we will also have to probably find out the velocity right here, and we can call that velocity to be v1, and we can call the velocity of the rocket at the very maximum position to be v2. Okay, so now we have a picture, we have more information regarding this. So looking at the first 16 seconds, of course you can understand that we are kind of dividing the problem in, again, part 1 and part 2. In the part 1 you have a set of values. So if I just look at looking at the first 16 second, we can now have a couple of equations. Okay, so the first equation gives us v1 equals to v0 plus 16 times a, right? And remember, a is positive number, but even if it was negative, we would not change the sign yet without knowing its number, without knowing the value. So since v0 is 0, this is nothing but 16a, and we can call this as our equation number 1. If we take the distance or displacement, if we take the position formula, we can call this as y1. Okay, so we can call y1 equals to y0, which is basically here, right? And that's also 0, plus v0 times 16 plus half times a times 16 squared. Simplifying this, because this is 0, this is also 0, it will basically become y1 equals to 128 times a. So that's our equation number 2. Then there was a third equation, which we may or may not need. So if you still want to be resourceful, want to keep that option, you could of course write down v1 square equals to, let me write it better, v1 square equals to v0 square plus 2a y1. And here we are always getting y1 because it's y1 minus 0, right? So because y equals to 0 here. Anyway, it would look like v1 square equals to 2a y1, and you would call it equation number 3 if you ever need it. But for now, if you were trying to solve a, you would not be able to solve a by looking at equation number 1 and 2, and not even 3, because you have too many variables. You have v1 that's not known, a is your desired solution, and you also don't know y1, right? So it will not help if you try to solve these 3 equations in order to find a. You will run into like roadblocks basically. All right, now we still have like a whole second part of the motion untouched, right? So for the last 4 seconds, right, 16 second it was accelerating, and then we have like 20 seconds. So from 16 to 20 second there is a 4-second time interval in which the rocket was doing something different, right? So the for the last 4 second we have acceleration, and we can call it a1. We have already named it a1, that is 9.8 meter per second squared downward, so it's a negative sign. And we can write down the equations with this, like v2 equals to v1 minus 9.8 times 4. 4 is the time, 9.8 minus 9.8 is the acceleration. So if you simplify this, this will become v2 equals to v1 minus 39.2, and you can call it equation number 4. And finally, you can also start looking at from this part to this part, right? You can call this as y2, or it's already given 5100. So if you look at the position formula, equation number 2, kinematics equation number 2, so it's like 5100 minus y1, right? This is delta y, equals to v1 times 4 minus half times 9.8 times 4 square, which is 16. So you could write it as 5100 equals to y1 plus v1 times 4 blah blah blah, but then you would basically add one more step, so I just wanted to save that step. So if you continue basically simplifying this, you are going to get 5100 minus y1 equals to 4v1 minus 78.4, and you can call it equation number 5. And if you closely look at equation number 5, now you can look at y1 and substitute the value of y1 from equation number 2, and you can look at v1, right? And that would basically also give you an expression in terms of a from equation number 1. So substituting from 1 and 2 in 5, what we get is basically 5100 minus 128a equals to 4 times 1664a minus 78.4, and you can solve easily now a from this equation, and that turns out to be 27 meter per second square. Okay, so we have successfully solved for the acceleration with which the rocket was moving initially, and that was asked in the question. Now you could go back and like solve all the other parameters, right? Like you can find actually y1, you can find v1, anything that you did not know before, you would be able to now calculate with the help of this acceleration that you found out. Okay, so just if you are curious, v1 is 16a, so 432 meter per second, and y1 is 128a, or 3456 meter. So you know like how far it was moving. It had moved during the first 16 seconds. You also know that how fast it was moving after 16 seconds. So I'm going to stop here, then we will probably be back with another problem after this, and then we would probably conclude chapter 191 problems, chapter 2 problems for 191 with the very last problem of the exercise.